Welcome back. Tonight, we are going to spend a long, slow evening together, exploring something you think you already understand. Cold. You know cold, or you think you do. You have felt it on your hands in January. You have opened a freezer and watched your breath cloud the air. You have walked outside in a winter coat, hunched against a wind that cuts straight through the fabric, and thought to yourself, "This is cold. This is real cold." But the truth is, you have never known cold. Not really. Not the way the universe knows it. Everything you have ever experienced as cold is, in the grand scale of the universe, barely different from boiling. The temperatures of a winter morning, an Antarctic ice sheet, even the inside of a kitchen freezer all sit warmly, comfortably, within the narrow band of temperatures where a human body can survive. A few dozen degrees below freezing at most. A tiny sliver of the possible. A warm, thin line on a scale that stretches down and down and down, far beyond anything that feels familiar. Outside that sliver, stretching into the dark, there are temperatures so extreme that the rules of matter begin to change. And the stranger direction, the more surprising direction, is the direction of cold. Tonight, we are going to travel to the coldest places in the universe. We will pass through the darkness between planets. We will land on the frozen surfaces of distant moons. We will drift through clouds of gas so cold they barely emit light. We will visit a nebula, dying at the edge of a constellation far beyond our solar system, that is colder than empty space itself. And then, slowly, we will travel back toward the Earth and down into human laboratories, where scientists have built quiet, careful machines that create temperatures more than 1 billion times colder than the darkness between galaxies. Temperatures so cold that atoms stop behaving like atoms. Temperatures so cold that reality itself seems to bend and stretch and dissolve into something that has no name. And finally, at the very end of the night, we will look forward into the long future of the universe, to a time when cold is all that remains, when every star has burned out, when every black hole has evaporated, when motion itself across the entire observable cosmos has slowed almost to a stop. This is the story of cold, the real story, the one that is much stranger than the cold you know. Take a slow breath. Settle in. You do not need to follow every detail. You do not need to remember any of this in the morning. Just let the sound carry you. And before we begin our journey, a gentle note. If you find these long, unhurried explorations useful for rest, consider subscribing to the channel. It is free, and it helps these nights continue. No loud music, no sudden jumps, no aggressive edits. Just long, calm walks through the universe, one quiet idea at a time. That is all we do here. And if you have been here before, thank you. It means more than you know. Now, let us begin with the simplest possible question. What is cold? Not what does cold feel like? Not what does cold do to us? But what is it, physically, when a thing is called cold? The answer is older than most people realize, and once you know it, cold becomes a much stranger thing than it seemed. Temperature is motion. That is the foundation. That is the quiet truth underneath every frost, every ice sheet, every winter morning you have ever known. The temperature of a thing is a measurement of how much its tiny parts are moving. The atoms, the molecules, the invisible, restless pieces that make up every solid, every liquid, every gas you have ever touched. Warm things are made of fast-moving particles. Cold things are made of slow-moving particles. That is all. That is the whole secret. When you place your hand on a warm mug of tea, the atoms in the ceramic are jiggling quickly. They bump into the atoms in your skin, and that bumping transfers energy, and your nerves translate that energy as warmth. When you place your hand on an ice cube, the atoms in the ice are jiggling slowly. Your faster-moving atoms bump into them, lose energy, and your nerves translate that loss as cold. Heat flows from fast to slow, always, without exception. It is one of the most reliable rules in the universe. This means that cold is not truly a substance. Cold is an absence. Cold is what happens when motion slows down. The slower the atoms move, the colder the object. And this leads to an astonishing question. What if the motion simply ran out? What if the atoms slowed, and then, finally, stopped? This is the question that haunted physicists for centuries. In the 1800s, scientists began to work backward from the behavior of gases. They noticed that as gases cooled, their volume shrank in a predictable way. By drawing a line through the data and extending it, they could predict the temperature at which a gas would, in theory, shrink to nothing. The temperature at which all motion would stop. That temperature turned out to be about minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit, or, in the scale used by physicists, 0 Kelvin. Absolute zero. The floor of the universe, the bottom of temperature, the point at which nothing moves at all. And here is the first strange thing about absolute zero. Nothing in the universe has ever reached it. Nothing ever will. This is not because our instruments are not good enough. It is not because we have not tried hard enough. It is because of a fundamental law of physics, one of the deepest truths we know about how matter works. It is called the third law of thermodynamics, and it states, in rough language, that absolute zero cannot be reached in a finite number of steps. You can get arbitrarily close. You can remove 99.999% of the thermal energy of a thing, and then 99.9999%. And then 99.99999%. You can approach absolute zero forever, but you cannot arrive. It is the asymptote of existence, a limit that is perfectly real and yet perfectly unreachable. The idea of absolute zero did not come all at once. It crept into science slowly, across centuries, the way most deep ideas do. In the 1600s, a French physicist named Guillaume Amontons built an early gas thermometer and noticed as he cooled it that the pressure inside dropped in a perfectly regular way. If he extended his line of measurements far enough, the line pointed toward a temperature at which the pressure would vanish entirely. Amontons did not call this point absolute zero. He did not have the language for it. But he wrote about it carefully, in papers that were mostly ignored by his contemporaries. In the 18th century, the Scottish chemist Joseph Black began to think about heat as a fluid that could flow from one body to another. His student, James Watt, used these ideas to design the steam engine that powered the Industrial Revolution. Heat, for the first time, was not just something you felt. It was something you measured, something you moved around, something you could count. In the 1800s, William Thomson, who would later be known as Lord Kelvin, gathered the scattered threads of earlier work. He saw that the behavior of gases, the motion of particles, and the thermodynamics of heat engines all pointed to the same thing: a temperature scale with a true zero. A scale that did not depend on the properties of water or alcohol or any particular substance, but on the motion of particles themselves. He proposed the scale that bears his name, the Kelvin scale. 0 Kelvin is absolute zero. Every degree Kelvin is the same size as 1 degree Celsius, so that water freezes at 273 Kelvin, and water boils at 373 Kelvin. The scale is clean and meaningful, and rooted in physics itself. Today, when scientists talk about very cold things, they always use Kelvin. Celsius and Fahrenheit both have zeros chosen for convenience around the range of human experience. Kelvin has a zero rooted in the universe's deepest laws. And this is worth remembering. When you hear a scientist say something is at 1 Kelvin, they are saying it is almost still, motion-wise, as deep as any known natural object. When they say something is at 38 picokelvin, they are saying it is trillions of times colder than any corner of deep space. The small numbers are not small temperatures in a familiar sense. They are a measurement of how close something has come to stillness itself. Kelvin's insight was not only technical, it was philosophical. He identified, with the help of many predecessors, an absolute reference point, a bottom to the universe, a place that exists in principle, even if it cannot be visited. Few things in physics are truly absolute. Most measurements, most reference frames, most laws are relative. Motion is relative. Time, in Einstein's relativity, is relative. Position is relative. But temperature, it turns out, is not entirely relative. There is a bottom, even if it cannot be reached. That alone is a remarkable discovery. And all of modern cold physics, every experiment we will talk about tonight, every laboratory, every laser, every careful refrigerator, rests on this foundation. A bottom that does not move. A floor that the universe cannot slide beneath. And a journey downward, step by step, to meet it. Take a moment with that idea. The universe has a floor that can be seen, measured, and predicted, but never touched. It is a boundary drawn in the physics of reality. Everything that has ever existed, everything that will ever exist, sits somewhere just above this floor, in the thin, warm air of motion. Your body, for instance. Your body is around 310 Kelvin, about 37 degrees Celsius. That is the temperature at which the complex chemistry of life can occur. If you cooled your body by just a few dozen Kelvin, down to around 273 Kelvin, the water inside you would freeze, your chemistry would stop, and you would die. The gap between living warmth and death is narrower than most people realize. Your kitchen freezer is around 255 Kelvin, minus 18 degrees Celsius, barely cold enough to preserve a bag of frozen peas, cold enough to hurt your hand if you touched it too long. But cosmologically, this is nothing. Cosmologically, this is almost lukewarm. The coldest temperature ever recorded on the surface of the Earth was minus 89.2 degrees Celsius. It was measured at the Vostok Research Station in Antarctica in July of 1983. In Kelvin, that is about 184. A cold so severe that human skin would freeze in under a minute. A cold that would shatter steel that had not been specially treated. A cold that no unprotected animal could survive. And even this, by the standards of the universe, is warm. This is important to understand, because it is the key to everything that comes next. We are, all of us, warm creatures. We live in a warm corner of a generally cold universe. Our skin is warm. Our blood is warm. Our homes are warm. Even the air around us, even the coldest winter air any human has ever walked through, is warm compared to the things we are about to visit. A being from a truly cold place, from the outer reaches of the universe where temperatures drop below 10 Kelvin, would look at Antarctica and wonder how anything so warm could possibly be called frozen. They would look at our bodies and see them glowing with heat. They would look at our planet and see a furnace. We are, all of us, creatures of a thin, warm band, and we have never really experienced what cold can become. Tonight, that changes. Tonight, we begin to travel outward, away from the warm earth, away from the sun, out into the darkness, past the planets, past the edge of the solar system, and out into the deep space between stars. And the first thing we will discover when we leave is that space itself has a temperature. A precise, measurable, strangely ancient temperature. It is not the ice-cold vacuum you might imagine. It is something more subtle, something quieter, something left over from the very beginning of the universe. Let us step out there together and see what the darkness actually holds. Let us travel outward, slowly, through the dark. Picture, if you can, our planet from above. A thin blue sphere wrapped in cloud, turning quietly on its axis, warm to the touch, from the light of the sun. A small island of warmth in the wide darkness. Now imagine the light dimming as you move away. The sun shrinks. The earth shrinks. The stars come out in every direction, not just at night, but always, because there is no longer any atmosphere to scatter the light and make the sky blue. Everything is black, and the stars are everywhere, and the darkness between them is deeper than any darkness you have seen before. This is where we are going. This is the road to the cold. But we need to build up to it, step by step. Because the cold you think you know is not the cold that waits out there, not even close. So let us step into the vacuum gently and ask a question that surprises most people. When you step into empty space, how cold is it actually? What temperature does space itself have? The answer, as you are about to discover, is both colder and warmer than you think. It is colder than anything you have ever touched, and warmer than the coldest thing humans have ever made. Let us find out how that can be. Part 2. The temperature of empty space. There is a common image of space. Perhaps you have it in your mind already. An astronaut drifting in a white suit, surrounded by absolute black. Cold stars. A frozen, silent vacuum. The word cold comes to mind almost automatically. Space is cold. Everybody knows that. But the truth is more interesting. Space, in the strict sense, does not have a temperature at all. Not the way a cup of tea has a temperature. Not the way a room has a temperature. Because temperature, remember, is the average motion of particles. And the vacuum of space, in between the stars, has very few particles. In some regions, fewer than 1 particle per cubic centimeter. Compare that to the air in your bedroom, which holds trillions upon trillions of particles in the same space. If there are almost no particles, there is almost no motion to measure. And if there is no motion to measure, there is no temperature in the ordinary sense. But space is not truly empty. Not anywhere. Not ever. And the thing that fills it, the thing that is always there, gives space a temperature of its own. An unusual, ancient temperature. A temperature that was set down a very long time ago and has been slowly falling ever since. To understand this temperature, we have to go back. We have to go back to the beginning of everything. About 13.8 billion years ago, according to the best evidence we have, the universe began. We do not know exactly how. We do not know exactly why. But the evidence is remarkably clear that the universe, as we now see it, emerged from a state of unimaginable density and heat. In the very first moments, the entire observable universe was packed into a region smaller than an atom. Every particle you have ever known, every atom in your body, every star you have ever seen, every galaxy, every empty stretch of dark space, all of it, compressed together, unthinkably hot. Then it expanded, rapidly at first, and then more slowly, and as it expanded, it cooled. This is a fundamental rule of gases. When you let a gas expand, it cools. If you have ever sprayed aerosol from a can and felt the can turn cold in your hand, you have felt this rule in action. The gas inside the can has lost some of its pressure, and the loss of pressure causes a loss of temperature. The universe, in its earliest moments, did the same thing. It was a single vast gas, and as it expanded, it cooled. It cooled rapidly. Billions of degrees, then millions of degrees, then thousands, and finally, just a few thousand. And at around 3,000 Kelvin, about 380,000 years after the beginning, something remarkable happened. The universe became transparent. Before that moment, the universe was so hot that electrons could not stick to atomic nuclei. They whizzed around freely, and this free electron soup scattered light in every direction, like a thick fog. If you had been there, you would have seen nothing but a dense, bright glow in every direction, because light could not travel in a straight line for long before being bounced by an electron. At 3,000 Kelvin, electrons slowed down enough to be captured. They settled into orbits around atomic nuclei, forming the first neutral atoms, mostly hydrogen. And suddenly, light could travel freely. The fog lifted. The universe became clear, and the last light, the very last light that was scattered before the fog cleared, began traveling outward in every direction. It has been traveling ever since. That light is still here, right now, this very moment. It is all around you. It has been passing through every square centimeter of space for nearly 14 billion years. And it is the reason that space has a temperature. We call it the cosmic microwave background. When that light was released, it had a temperature of about 3,000 Kelvin, the glow of red hot metal. But as the universe continued to expand, the light stretched with it. Its wavelength grew longer and its temperature fell. It went from visible light to infrared to microwave. It cooled slowly over billions of years. It is still cooling today, and today that ancient light, the oldest light in the universe, has a temperature of 2.725 Kelvin. Let us pause there. 2.725 Kelvin. That is about minus 270 degrees Celsius, or minus 455 degrees Fahrenheit. This is the temperature of space, the temperature of the background, the temperature that surrounds you, and every planet, and every star. The temperature of the emptiness between everything. It is extraordinarily cold by any standard you would use in daily life. 170 degrees colder than Antarctica. 250 degrees colder than your freezer. Only about 2.5 degrees above the lowest possible temperature that physics allows. And yet, as we will see, it is not the coldest thing in the universe. Not by a long way. But before we go on, it is worth sitting with the strangeness of what we have just said. The emptiness around you has a temperature, not because it contains particles that are moving slowly, but because it is bathed in ancient light. Light that was released when the universe was still young. Light that has been traveling without stopping for almost the entire age of everything. That light is still here, right now, passing through the wall of your room, passing through your body, passing through the pillow under your head. It is impossibly faint. It is invisible to your eyes. You would need a delicate microwave antenna to detect it. But it is there. It is everywhere. It has been called the echo of creation, and it gives space its temperature. Scientists discovered this light almost by accident. In the 1960s, two researchers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. They had taken over a large horn-shaped antenna that was originally built for satellite communication, and they were trying to use it for radio astronomy. To do their work, they needed to get rid of every possible source of background noise. Any faint hiss in the antenna would ruin their measurements. But there was a hiss they could not get rid of. It came from every direction in the sky, equally at all times of day and night. It did not change with the seasons. It did not change when they pointed the antenna at different stars. It was just there, a faint, uniform, persistent whisper. They cleaned the antenna. They checked the wiring. They even climbed inside and scrubbed out a nest of pigeons that had made a home in the horn. None of it helped. The hiss remained, faint, cold, and everywhere. What they were hearing, though they did not know it at first, was the cosmic microwave background, the oldest light in the universe, falling into their antenna, sounding like soft static. Nearby, at Princeton, a different group of physicists had predicted this exact signal. They had reasoned, from the physics of a hot early universe, that there should be a cooled remnant light bathing all of space, at a temperature of just a few Kelvin. When they heard about the mysterious hiss at Bell Labs, the pieces fell into place. The two groups met. The discovery was announced. And in 1978, Penzias and Wilson received the Nobel Prize in Physics for it. The discovery at Bell Labs was only the beginning of humanity's relationship with the cosmic microwave background. Over the decades that followed, scientists built increasingly sensitive instruments to map this ancient light, not just to measure its average temperature, but to measure the tiny ways in which its temperature varies across the sky. Because the background is not perfectly uniform. Not quite. If you look at it carefully, with instruments precise enough, you find that some patches of sky are very slightly warmer than others, and some are very slightly cooler. The differences are tiny, only a few parts in 100,000, but they are there. They are real, and they carry information of enormous value. The first satellite dedicated to mapping the cosmic background was called COBE, the Cosmic Background Explorer. It launched from Earth in 1989, orbited the planet at a safe distance, and mapped the whole sky in microwave light. COBE measured the background with unprecedented accuracy. It confirmed that the background is a near-perfect thermal spectrum, exactly what you would expect from a cooled early universe. And it detected, for the first time, those tiny variations, the faint hot and cold spots in the ancient light. The scientists in charge of COBE were George Smoot and John Mather. They won the Nobel Prize in Physics in 2006 for their work. COBE was only the beginning. In 2001, NASA launched a more advanced satellite called WMAP, the Wilkinson Microwave Anisotropy Probe. WMAP mapped the cosmic background at higher resolution and sat for 9 years in an orbit far from the Earth, where our planet's own thermal emission would not contaminate its measurements. WMAP revealed the structure of the tiny variations in stunning detail. Patches of light, slightly hotter, slightly cooler, distributed across the sky in a pattern that carried the fingerprints of the universe's earliest history. Then, in 2009, the European Space Agency launched the Planck satellite. Planck was even more sensitive than WMAP. It operated for 4 years, returning the most detailed map of the cosmic background ever made. And from that map, scientists have extracted an extraordinary amount of information, the age of the universe more accurately than ever before, the proportion of ordinary matter, and dark energy, the shape of space, the conditions in the first tiny fraction of a second after the Big Bang, when the universe was only a quantum fluctuation, a whisper in the earliest moments. Planck also confirmed to exquisite precision that the average temperature of the cosmic microwave background is 2.725 Kelvin, very slightly cooler in some directions, very slightly warmer in others. The average, remarkably stable, remarkably cold. What we see in those tiny variations across the whole sky are the seeds from which galaxies later grew. The slightly denser patches in the early universe, where gravity pulled just a little harder, eventually became the clusters of galaxies we see today. The slightly less dense patches became the great voids between them. Every structure in the modern universe, every galaxy, every star, every planet, every living creature, has its origin in one of those tiny, cold, or warm spots, imprinted in the background light 13 billion years ago. It is an extraordinary thought. The soft glow of microwave light, bathing all of space at just under 3 degrees above absolute zero, carries within it the entire history of how the universe became what it is. Its tiny variations are the oldest photograph ever taken. They record a moment when nothing existed yet. No stars, no galaxies, only a cooling, dimming plasma, just becoming transparent. And that photograph is cold. 3,000 Kelvin at the moment of release, 2.7 today. Still cooling. The cosmic microwave background is, in this sense, two things at once. It is the temperature of space in our present time, and it is the last light of an earlier, hotter universe, stretched out across billions of years until its warmth has all but vanished. Both things are true. Both are the same light. Both are, in a way, the same cold. What they had discovered was, in a very real sense, a kind of thermometer for the universe itself. Every point of space, in every direction, reads out a temperature of 2.725 Kelvin. Very slightly warmer in some patches, very slightly cooler in others. These tiny variations are themselves the seeds of galaxies and clusters. They are the faint, ancient fingerprints of the structures that formed billions of years later. But the overall temperature is remarkably uniform. Space, almost everywhere we look, is 2.725 Kelvin. This has a practical consequence that you might not expect. It means that no object in the universe, left alone for long enough, can naturally cool below this temperature. It is the floor of passive cooling. If you leave a rock in the middle of the deepest void, far from any star, far from any galaxy, it will slowly radiate heat into space, cooling over time. But it will cool only until it reaches the temperature of the background itself. After that, the light from the background will heat it just as much as it loses. Equilibrium. 2.725 Kelvin is the passive floor of the universe. Nothing can passively get colder than that. Everything that is colder than that has been made colder, either by an unusual physical process or by a patient, careful effort. This leads to one of the most surprising facts in astronomy. There are places in the universe, real places, natural places, that are colder than the cosmic microwave background itself, colder than space. colder than the ancient light that bathes everything. This should not be possible in a simple universe. And yet it is. To understand how, we will have to travel to a dying star. Slowly, gently, no hurry. But before we get there, we have another, smaller question to answer. A question that confuses many people. If space is only 2.725 Kelvin, how do astronauts survive in it? Because when an astronaut steps outside the International Space Station, the temperature of the space around them is about 270 degrees below Celsius. And yet astronauts do not instantly freeze. They can float there for hours. Why? The answer is that space cools things very differently than air does. When you step outside on a cold morning, the air around you is filled with fast-moving particles. Those particles collide with your skin, carry heat away, and replace the warm air near your body with new, cold air. The process is called convection, and it is brutally efficient. In a cold room, in a cold wind, your body loses heat very quickly, because every square centimeter of your skin is in contact with a sea of eager, heat-stealing particles. In the vacuum of space, there is almost no such sea. There are almost no particles touching your skin. So, convection barely works at all. The only way to lose heat in space is by radiation. Your body and every warm object glows faintly in infrared light. It radiates that light outward into the darkness, and that light carries energy away. Over time, a body in space will cool because it is always radiating. But the process is slow, much slower than in air. An astronaut in space does not freeze in minutes. They cool gradually. In fact, the larger problem for astronauts on the sunlit side of the station is not that they will freeze, but that they will overheat, because there is no air to carry away the heat their bodies produce. On the dark side, they cool, but slowly. Space, in other words, is not cold the way a winter wind is cold. It is cold in a quieter, slower way. It drains heat the way a very thick, very patient blanket might, imperceptibly, over time. This is another piece of the story of cold. The way in which a thing cools matters. A cold thing can drain your warmth quickly through contact, or slowly through radiation, or it can seal it in if the thing between you and the cold does not allow heat to move. The universe is full of this kind of subtle accounting. Every object is glowing faintly, losing heat. Every object is catching some of the cosmic background, gaining heat. The balance of these two flows determines the temperature it eventually reaches. And, in most places, that balance settles at around 2.725 Kelvin. The ambient cold of the universe, the whisper of the oldest light. It is cold, but it is not the coldest. It is only the beginning. Because somewhere in the direction of the constellation Centaurus, about 5,000 light-years from Earth, in the slowly expanding cloud of a dying star, there is a place where matter has found a way to grow colder than the background itself. A place that should not exist, and yet does. Let us travel there next. Part 3. Nature's Record Holders. Before we fly to the coldest natural place in the universe, let us walk slowly through our own solar system and look at the cold in our own neighborhood. Because even here, close to home, there are places colder than anywhere on Earth. Much colder. Let us begin by leaving the sun behind. The sun is a small warm thing in the grand sense, a yellow dwarf star about 150 million kilometers from Earth. Close enough to warm our planet to an average temperature of about 15 degrees Celsius. Close enough to keep our oceans liquid and our air from falling as snow. every drop of warmth you have ever felt, other than the small amount produced by your own body and the heat of the earth itself, came from the sun. But the sun's warmth does not extend forever. It falls with distance, gently but inexorably, according to a mathematical rule. Double the distance, and the warmth drops to 1/4. Triple the distance, and it drops to 1/9. Move outward by 10 times, and the warmth drops to 1/100th. This means that the farther you go from the sun, the colder the planets become, and the solar system is much bigger than most people realize. Mercury, the closest planet, is scorched on one side and freezing on the other. Its night side can drop to about 100 Kelvin, which is 173 degrees below 0 Celsius, colder than anywhere on Earth. A record that would be broken in just a moment by the next world on our tour. Venus, the second planet, is almost uniformly hot. A thick atmosphere of carbon dioxide traps the sun's heat in a runaway greenhouse, keeping the surface at around 740 Kelvin. Hot enough to melt lead. Hot enough that a probe landing on Venus has only minutes to work before it cooks. No cold defined here. Earth, your home, sits in the narrow livable zone, a warm blue island. We know it well. Mars, the fourth planet, is colder than Earth, but not by as much as you might guess. Its thin atmosphere cannot trap heat well, and the planet is farther from the sun. Average surface temperatures are around 210 Kelvin. On a winter night at the poles, it can fall to 140 Kelvin. That is colder than any point on Earth, but still not the coldest in the solar system. Beyond Mars, we cross a line. We leave the rocky planets. We cross the asteroid belt, a thin ring of floating rubble, and we enter the outer solar system. And here the cold begins in earnest. Jupiter, the first of the giants, is a world of clouds. Its upper atmosphere sits at about 160 Kelvin. Not extreme, but notably cold. The temperature depends on depth, with the lower layers, deep beneath the visible clouds, growing hotter due to internal heat. Saturn, with its rings, is colder still. Its cloud tops are around 134 Kelvin, about minus 140 degrees Celsius. Uranus, a pale blue-green world tilted on its side, is colder, much colder. Its cloud tops drop to about 76 Kelvin, colder than any natural surface we have yet visited. But Neptune is where the real cold begins. Neptune is the farthest of the major planets. A deep blue, wind-lashed giant, over 4.5 billion kilometers from the sun. Its cloud tops sit at about 72 Kelvin, only a few degrees warmer than Uranus. But orbiting Neptune is a moon, a curious active moon, which holds a record worth noting. Its name is Triton. Triton is the largest of Neptune's moons, and one of the coldest bodies ever directly measured by a spacecraft. When Voyager 2 flew past in 1989, it measured Triton's surface temperature. The reading was astonishing. 38 Kelvin, about minus 235 degrees Celsius. At the time, this was the coldest natural surface temperature ever recorded in our solar system. 38 Kelvin. Only 38 degrees above the absolute floor of the universe. Triton has a thin nitrogen atmosphere. At this temperature, nitrogen freezes. Water, at this temperature, is harder than rock. Ice on Triton is a building material, like stone on Earth. It cracks, it flows, it forms mountains. The landscape is eerie, pale pink and pale yellow, crisscrossed by strange ridges and plains. Voyager captured images of geysers of nitrogen, cold eruptions shooting up from the surface, rising kilometers into the thin sky before falling, back down as frost. Triton is cold enough to change the way matter behaves, and still it is not the coldest place in the solar system. Beyond Neptune, in the Kuiper belt, there are countless smaller worlds. Pluto, the former ninth planet, is one of them. Pluto's average surface temperature varies depending on its orbit, because Pluto has a long elliptical orbit that sometimes brings it closer to the Sun and sometimes flings it far out. At its coldest, the surface of Pluto is around 33 Kelvin, colder than Triton. Cold enough that even nitrogen and methane freeze into vast, glittering plains. When the New Horizons probe flew past Pluto in 2015, it sent back images of sharp mountains made of water ice, hard as granite at those temperatures, and broad, flat valleys filled with soft nitrogen ice that flowed slowly over millions of years. The pictures were beautiful. Pale, strange, and distant. A world wrapped in the deepest silence, untouched by any warm wind. And still, Pluto is not the coldest. The coldest place in our solar system is, surprisingly, much closer to home. It is on the Moon, not the bright side, not the lit valleys, but certain craters at the lunar poles, craters whose floors have never seen sunlight. Not once. Not for billions of years. These craters sit at the bottom of very deep bowls, surrounded by high walls. The sun, from those latitudes, hangs low on the horizon and never rises. Its light has never reached the floor. These are called permanently shadowed regions, and in the coldest of them, the temperature has been measured at around 25 Kelvin. That is minus 248 degrees Celsius. 25 Kelvin. Colder than Pluto. Colder than Triton. On our own moon. These regions are of intense interest to scientists because in their permanent darkness, water ice has been preserved for billions of years. Any comet or icy meteor that struck the moon and scattered water, any vapor brought by some ancient process, would have settled into the coldest spots and frozen there, unable to escape. Ice that may be older than any on Earth. Ice that is, in a very real sense, a record of the solar system's earliest days. Future astronauts, if they ever walk into those craters, will be walking into some of the oldest preserved material in the neighborhood of the Sun, and they will need the best insulation ever built to survive in it. Among the most studied of these lunar shadowed regions is a crater at the South Pole called Shackleton. It is named after the polar explorer Ernest Shackleton. The crater is about 21 kilometers across and over 4 kilometers deep. Its rim is illuminated by the sun for more than 80% of the lunar year, making it one of the brightest places on the moon. But its floor, bathed in the shadow of that rim, has never seen the sun. Not once since the crater formed, billions of years ago. NASA's Lunar Reconnaissance Orbiter, a satellite that has been circling the moon since 2009, has mapped these shadowed regions in extraordinary detail. Using an instrument called Diviner, the orbiter measures the thermal emission from the lunar surface, allowing scientists to determine the temperature of every patch of ground below. And the coldest readings ever recorded come from the floors of the darkest craters. Around 25 Kelvin, minus 248 degrees Celsius, a temperature so extreme that future astronauts, if they ever walk into those craters, would need insulation more advanced than anything astronauts on the International Space Station use today. Standard spacesuits are designed for environments that hover around 250 Kelvin. The shadowed craters would require new technology, heated suits, active thermal regulation, careful mission planning to avoid spending too long in any one place. And yet these craters are among the most valuable places in the solar system, for science and for future exploration. Because of the trapped ice, they may be the key to a long-term human presence on the Moon. Ice can be melted for water. Water can be split into hydrogen and oxygen for breathable air and rocket fuel. The permanently shadowed regions are not just cold curiosities. They are potential refueling stations for journeys to Mars and beyond. When humans finally descend into those craters, they will be entering a place that has been undisturbed for longer than complex life has existed on Earth. A silent, perfectly dark, perfectly cold hollow in the lunar surface. No wind, no atmosphere, only rock and ice waiting for visitors. So that is the cold of our solar system. From the warm blue Earth to the hot surface of Venus, to the frozen plains of Triton and Pluto, to the shadowed craters of our own moon at 25 Kelvin. But the solar system is a small, warm pocket in a vast galaxy, and the galaxy is a small, warm patch of a vast universe. The real cold is out there, among the stars. Let us travel farther. When you leave the solar system, the warmth of the sun falls away completely. There is no longer any local source of heat that matters. You drift between stars, across distances so vast that they are difficult to imagine. And everywhere around you, the cosmic microwave background glows softly at 2.725 Kelvin. The background temperature of the universe, the floor of passive cooling. In this deep dark, there are clouds, vast, slow-moving clouds of gas and dust, sometimes stretching across hundreds of light years. They are called molecular clouds because their hydrogen is cool enough to combine into molecules of hydrogen gas instead of existing as isolated atoms. Molecular clouds are the cradles of stars. Deep inside them, gravity draws matter together, slowly collapsing into dense cores that eventually ignite as new suns. But before they ignite, the clouds themselves are some of the coldest large-scale structures in the galaxy. 10 Kelvin in places, sometimes even lower, only a few degrees warmer than the background. They are cold because they are dense enough to shield their interiors from starlight. Dust grains absorb the light from nearby stars, warming up slightly themselves, but leaving the deep interior almost untouched. The gas inside these pockets has very little energy. It moves slowly. It radiates slowly. It cools and cools and cools. Some of the coldest measured molecular clouds in our galaxy sit at around 8 to 10 Kelvin. Most are a bit warmer, around 20 Kelvin. All of them are colder than anywhere in our solar system outside those shadowed lunar craters. But even these vast clouds are not colder than the background. Not truly. They are close, but they are gently heated by the sea of microwaves that bathes them. They cannot, by themselves, fall below the temperature of the cosmic background. And yet, there is one place, one known place in the entire known universe where natural matter has grown colder than the cosmic microwave background itself. It is called the Boomerang Nebula. In the southern sky, in the constellation Centaurus, about 5,000 light-years from Earth, there is a dying star. It is not a large star, not famous, not especially bright. But it is doing something extraordinary. It is blowing itself apart in slow motion, and the gas it is expelling is colder than empty space. The Boomerang Nebula was first noticed in the 1970s by astronomers using radio telescopes in Australia and Chile. Later, in the 1990s, it was imaged in detail by the Hubble Space Telescope. The pictures are striking. two lobes of pale, softly glowing gas arranged in a symmetrical hourglass shape. The name came from an early observation that suggested a slight asymmetry, like a boomerang. But the truly remarkable thing about the Boomerang Nebula is not its shape. It is its temperature. Astronomers measured the nebula's temperature by looking at how it absorbed and emitted specific wavelengths of light. And the answer was clear. The expanding gas of the Boomerang Nebula is about 1 Kelvin. Some measurements give 1.15. Some give as low as 1 Kelvin flat. In round numbers, the gas is about 1 degree above absolute zero, colder than the cosmic microwave background, colder than empty space, colder than any other natural object ever measured. How is this possible? The background is warming everything. How can the gas fall below it? The answer is a beautiful piece of physics. The gas is expanding very rapidly, about 160 kilometers per second. That is faster than any other known outflow of this kind. And when a gas expands, it cools. The expansion does work against the surrounding pressure, and that work drains energy from the gas itself. In the Boomerang Nebula, the gas has been expanding for about 1,500 years at this phenomenal speed. Over that time, it has been cooling rapidly. So rapidly that the rate of cooling from expansion exceeds the rate of warming from the background. The result is a region of space where the gas is colder than the light around it, colder than the universe's floor of passive cooling. It is a refrigerator running in the dark, far from any star that can warm it. No one knows exactly why the Boomerang Nebula is expanding so fast. The central star is dying, shedding its outer layers, but most such stars produce slower outflows. The Boomerang is unusual. It may have had a close companion star that was consumed or stripped, transferring orbital energy into the outflow. It may have undergone an unusual kind of thermal pulse. The exact cause is still debated, but the result is extraordinary. A natural refrigerator in deep space, gas at 1 Kelvin, dust at 1 Kelvin, the coldest natural place ever found, and it is beautiful. The Hubble images show a soft, faintly glowing structure, illuminated by starlight filtering through the nearly transparent gas. The outer regions blur into the darkness around it. The shape suggests gentle motion, but the speeds involved are huge. Standing at the edge of the nebula, you would feel no wind, see no motion, hear nothing. Sound cannot travel in such thin gas. The motion is faster than the muzzle velocity of a bullet, but it is silent, invisible, and uniform. And it is a degree above the bottom of everything. The precise mechanism of the boomerang's cold is still being studied. The star at the center is a dying red giant, shedding its outer layers as many old stars do. But the speed at which it is shedding them is anomalously high. Most similar stars produce outflows at 15 or 20 kilometers per second. The boomerang's outflow is 10 times faster than that. Astronomers have proposed several explanations. The most popular suggests that the dying star had a close companion, a second star orbiting very near, which dipped inside the outer layers of the red giant. As the companion star interacted with the surrounding gas, it transferred orbital energy to the outflow, giving the escaping gas a tremendous kick. The companion star may have been entirely consumed during this process, leaving behind only the visible dying star that astronomers see today. There are other proposals. A strange kind of internal nuclear pulse, an unusual magnetic configuration, a very rapid phase of stellar evolution that only lasts a few thousand years, which is why similar systems are rare. Observations with the Atacama Large Millimeter Array located high in the Chilean Andes, have confirmed the nebula's extreme temperature and revealed more details of its structure. But the exact history remains one of astronomy's small, beautiful puzzles. And it is worth noting that the Boomerang is not the only cold nebula. There are others, known variously as preplanetary or protoplanetary nebulae, that also contain unusually cold gas. Most of them are slightly warmer than the Boomerang, but a few approach its record. Some astronomers suspect that there may be dozens or hundreds of similar cold pockets scattered through our galaxy. Most of them have never been surveyed in detail. Most of them remain, for now, unseen. The universe contains more surprises than we have yet had time to measure. You can picture it if you try. The central dying star, white with heat, surrounded by a vast expanding shell of quiet frozen gas. The gas is so cold that most molecules in it have collapsed into their lowest energy states. Even the vacuum of deep space is warmer. The nebula is a pocket of cold, drifting through the galaxy, drifting past distant stars, drifting onward through the dark. It will not last forever. As the gas expands further and thins out, the cooling will slow, and eventually the background radiation will warm it back up to 2.7 Kelvin. The pocket of anomalous cold will fade. In a few thousand years, the nebula will have warmed to match its surroundings. It will be ordinary again. But right now, tonight, as you lie in the warmth of your bed, the Boomerang Nebula is still cold. Still 1 Kelvin above the floor. Still the coldest natural place in the universe. It is a quiet wonder, a cosmic cold that should not exist, and yet does for a few hundred years of cosmic history, in one small corner of one spiral arm of one galaxy. And it is, strangely, a kind of comfort. The universe is not uniform in its cold. There are islands, there are pockets, there are places where, by some accident of motion and expansion and dying stars, the rules bend and the temperature drops below the background floor. But even 1 Kelvin is not the coldest thing humans have ever measured. In fact, the very coldest temperatures in the universe are not in some distant nebula. They are on Earth, in laboratories, in glass chambers and vacuum pumps and the quiet hum of refrigerators more delicate than any refrigerator you have ever seen. Humans have made things colder than the Boomerang Nebula, and they have done it on purpose, patiently, carefully, with tools so sensitive that the slightest breath of heat would ruin the experiment. In the next section, we travel home, and then down into those laboratories, into the strange, quiet places where people have pushed matter colder than anywhere in nature. Let us begin our descent. Part 4. Colder than space itself. Human laboratories. The coldest place in the universe is not in space. It is on Earth, in buildings, in rooms, in thin glass chambers surrounded by nested shields and magnets and quiet, silent machines that do nothing but remove energy from atoms, one small piece at a time. Humans have made things colder than the Boomerang Nebula. Much colder. So cold that they are, by every available measurement, the coldest material objects the universe has ever known. Let us travel slowly into those laboratories and see how it is done. The story begins in the early 20th century, when scientists first learned to liquefy gases that had always been gases on Earth: oxygen, nitrogen, hydrogen. By compressing them hard enough and then releasing them, and by cooling them with each cycle, physicists turned each of these gases into a liquid. Liquid oxygen at 90 Kelvin, liquid nitrogen at 77 Kelvin, liquid hydrogen at 20 Kelvin. And then, in 1908, A Dutch physicist named Heike Kamerlingh Onnes succeeded in liquefying helium. Helium is the hardest to liquefy because its atoms interact with each other only very weakly. It does not want to stick together. It does not want to be a liquid. But with enough cooling and enough pressure, even helium surrenders. At about 4.2 Kelvin, helium becomes a liquid. 4.2 Kelvin. Colder than most of the solar system. Colder than almost any natural object except the Boomerang Nebula. And at this temperature, Onnes discovered something remarkable. When he cooled a sample of mercury to very low temperatures, he found that its electrical resistance dropped, not gradually, but suddenly, all the way to zero. At a certain critical temperature, the mercury became a superconductor. Electricity could flow through it without any resistance at all. This was the first discovery of superconductivity, and it hinted at something deeper, that when you cool matter close enough to absolute zero, new and strange things happen. Rules change. The ordinary behavior of materials gives way to phenomena no one had predicted. Cooling, in other words, is a way of exploring the universe. The colder you can make a thing, the more hidden physics you can reveal. And so began a slow, patient race to the bottom. To cool matter as close to absolute zero as possible. The first decades of progress were slow. By clever engineering with helium, researchers could reach a few tenths of a Kelvin, but getting below that required entirely new methods. In the mid-20th century, two key techniques emerged. The first was called adiabatic demagnetization. It worked by aligning the magnetic spins of atoms in a strong magnetic field and then slowly removing the field. As the spins relaxed, they absorbed energy from the surrounding material, cooling it. With this technique, scientists reached the millikelvin range, thousandths of a Kelvin above absolute zero. Millikelvins, 1,000 times colder than liquid helium, 1,000 times colder than anywhere in our solar system, except possibly the inside of certain very quiet, very carefully built refrigerators. And then, in the 1980s, a new method revolutionized cold. It was called laser cooling. Here's the idea, stripped of equations and simplified. A photon of light has momentum. When a photon hits an atom, it transfers a tiny amount of that momentum. If you arrange laser beams so that they strike atoms from all sides, and you tune the frequency of the lasers just right, you can create a situation where atoms moving toward a laser absorb the light, but atoms moving away do not. The effect is that moving atoms are slowed down by the light. Each photon is a tiny push, but millions of photons per second can add up to a significant deceleration. Laser cooling was developed in the 1980s by scientists including Stephen Chu, William Phillips, and Claude Cohen-Tanuji. They shared the Nobel Prize in Physics in 1997 for their work. Using laser cooling, they could slow atoms to speeds of a few centimeters per second, compared to their normal speeds of hundreds of meters per second at room temperature. And slower atoms mean colder atoms. Much colder. With laser cooling, scientists reached temperatures of microkelvins, millionths of a Kelvin above absolute zero. Let us pause on that. Millionths of a degree. If the Boomerang Nebula is 1 Kelvin, microkelvins are 1,000,000 times colder. Nothing in nature has ever been measured at microkelvin temperatures, as far as we know. This is a realm only humans have visited, and it was still not the limit. In 1995, at a laboratory at the University of Colorado, two scientists named Eric Cornell and Carl Wyman achieved something physicists had dreamed of for 70 years. They cooled a gas of rubidium atoms to less than 170 nanokelvins, 170 billionths of a Kelvin. And at that temperature, the atoms did something unprecedented. They merged. They did not collide. They did not crystallize. Something far stranger happened. At this unimaginably low temperature, the individual atoms lost their individuality. Their quantum wave functions overlapped and combined into a single shared quantum state. The cloud of atoms, which contained thousands of individual particles, behaved as a single object. It moved as one. It responded to stimulation as one. It was, in effect, a new state of matter. This was the Bose-Einstein condensate. It had been predicted 70 years earlier by Albert Einstein, based on work by the Indian physicist Satyendra Nath Bose. But nobody had been able to cool atoms cold enough to see it. Nobody until 1995. Cornell and Weizmann, along with Wolfgang Ketterle at MIT, who achieved the same result months later, won the Nobel Prize in Physics in 2001. And at 170 nanokelvins, humanity crossed a new threshold. We were no longer just cooling matter. We were unlocking new forms of it, new states that could not exist at higher temperatures, states in which atoms shared identities, states in which quantum mechanics, usually hidden in the smallest scales, became visible to the naked eye. But the cold did not stop there. Since 1995, laboratories around the world have pushed the record colder and colder. New methods were invented. Evaporative cooling, in which the hottest atoms are selectively removed, leaving only the coldest behind. Sisyphus cooling, in which atoms climb repeating potential hills and lose energy on each climb. Gravity-assisted cooling, in which atoms are allowed to fall freely and their kinetic energy measured and subtracted. By the 2010s, temperatures of picokelvins had been reached, trillionths of a Kelvin. At picokelvin temperatures, atoms move at a few millimeters per second, cold almost beyond description. And then the story moved off Earth entirely. Because there is one thing that makes laboratory cooling very difficult on our planet. Gravity. An atomic cloud at picokelvin temperatures is so fragile that even the faintest force can disturb it. And gravity isn't faint. As soon as you release such a cloud from its magnetic trap, gravity pulls it apart in milliseconds, before you can finish your measurement. To get longer observation times, scientists took their experiments off the planet. In 2018, an instrument called the Cold Atom Laboratory was installed aboard the International Space Station. In microgravity, the atomic clouds do not fall. They drift. Free of the tug of gravity, they can be cooled for longer, held for longer, studied for longer. And in the Cold Atom Lab, and in similar instruments that followed, record-breaking temperatures have been measured. Temperatures around 38 picokelvins. Some recent experiments have reported even lower, in the range of 10 picokelvins or below. 38 picokelvins. 38 trillionths of a degree above absolute zero. Let us try to compare that to what we have seen already. The Boomerang Nebula, the coldest natural place in the known universe, is at about 1 Kelvin. The cold atom experiments on the space station are at about 38 picokelvin. That is 100 billion times colder than the coldest natural object, roughly 10 billion times colder than deep space. The coldest laboratory cold is, by every measure, many times colder than anywhere in the known universe outside human hands. Somewhere, right now, inside a careful glass chamber orbiting the Earth, there is a small cloud of atoms that is, by every metric we can apply, the coldest material ever to exist. colder than any star, any nebula, any void, colder than the universe has ever been, even moments after the Big Bang. And it is just sitting there, barely moving, waiting, being studied by patient scientists who send signals up from the ground and watch the results come back down. A small, quiet, cold heartbeat. There is another project worth mentioning. Unlike the Cold Atom Lab, which cools a tiny cloud of atoms, this experiment cools a large chunk of matter. It is called Cuore, and it sits deep underground in an Italian mountain called the Gran Sasso. The researchers of Cuore wanted to search for a rare kind of radioactive decay, and to do so they need to cool an enormous crystal of tellurium dioxide to as cold a temperature as possible, for as long as possible. The crystal weighs nearly a ton. 988 kilograms of dense, careful crystal. It is cooled using a dilution refrigerator, a large and intricate device that uses the properties of helium-3 and helium-4 mixtures to reach temperatures below 1/10 of a Kelvin. In Cuore, the ton of crystal is kept at about 10 millikelvins, 10,000ths of a degree above absolute zero. This is colder than anywhere else in the known universe at that scale. A full ton of material, kept at a temperature below every natural object we have ever found. Kept there for months at a time, studied continuously. Cuore is, as far as we know, the coldest cubic meter in the universe. Why do we do this? Why do scientists build elaborate refrigerators that would not exist anywhere in nature? Cool matter to temperatures that would take the universe many times its current age to achieve on its own, and then do it over and over in dozens of laboratories around the world. There are many reasons, some practical, some beautiful. At low temperatures, quantum effects become visible. The weird behaviors of the very small, usually hidden under the noise of thermal motion, emerge. Superconductivity, superfluidity, quantum entanglement over macroscopic scales. By studying matter near absolute zero, scientists can see quantum mechanics in action, almost with the naked eye. At low temperatures, unusual states of matter can form. Bose-Einstein condensates, fermionic condensates, superfluids that flow without friction and climb up the walls of their containers. Matter does things at low temperatures that it cannot do anywhere else. To understand the full range of physics, we must be able to reach these temperatures. At low temperatures, we can search for rare signals. Faint interactions that would be drowned out by thermal noise at higher temperatures become detectable when the background is quiet. Experiments like Cuore, searching for rare nuclear decays, or dark matter experiments like xenon and LUX, all rely on deep cold to keep their detectors quiet enough to catch faint signals from the universe. At low temperatures, we can build quantum computers. Quantum bits, or qubits, are delicate. They lose their quantum state if they are perturbed by thermal motion. The coldest quantum computers in the world, at major laboratories run by companies and research institutions, operate at about 10 to 20 millikelvin, colder than most of the known universe, in a matter sense. And at low temperatures, we can build atomic clocks of unimaginable precision. The coldest atomic clocks can measure time so accurately that they would gain or lose less than a second over the entire age of the universe. They can detect the tiny gravitational redshift caused by moving them up by 1 centimeter, because time flows very slightly slower near the ground. This is not a philosophical idea. This is a direct measurement made with a machine on a table in a basement. Let us linger on atomic clocks for a moment, because they are perhaps the most practical application of deep cold in everyday life. A clock, in the end, is anything that ticks regularly. The earliest clocks used pendulums. Later, clocks used quartz crystals, which vibrate at a very steady frequency when a small electric signal is applied. These clocks are accurate to about 1 second per month. Good enough for ordinary timekeeping. Not good enough for satellites, for scientific measurements, or for the subtle tests of physics we care about. Atomic clocks use atoms themselves as their pendulums. Specifically, they use the natural frequencies at which atoms absorb and emit light. Each kind of atom has its own precise set of frequencies. Cesium atoms, for example, transition between two particular energy states at exactly 9,192,631,770 cycles per second. That is the official definition of a second in international standards. 1 second is that many cycles of the cesium transition. It is a physical, atomic definition, not a human one. A cesium atomic clock works by catching a beam of cesium atoms and tuning a microwave field to match their natural frequency. When the frequency is exactly right, the atoms absorb energy and change states. The clock counts the cycles of the microwave field, and each 9 billion plus cycles is, by definition, 1 second. The accuracy of a cesium atomic clock depends on how cleanly the atoms can be measured. And cleanliness, in this context, means how slowly the atoms are moving. Fast-moving atoms, hot atoms, give a blurry measurement. The frequency of their transition is smeared out by the Doppler effect, like a siren that changes pitch when an ambulance rushes past. Slow-moving atoms, cold atoms, give a sharp measurement. The frequency is clear. The clock is precise. This is why the most accurate atomic clocks in the world use laser-cooled atoms. The atoms are slowed to speeds of a few centimeters per second, then launched upward in a kind of atomic fountain. They rise, fall back down under gravity, and during their brief free fall they are interrogated with microwaves. The slower they move, the longer the interrogation, the more precise the measurement. In recent years, even more accurate clocks have been built using optical transitions in other atoms, like strontium or terbium. These clocks use visible light instead of microwaves, and their transitions are hundreds of thousands of times faster. Optical lattice clocks, as they are called, are the most accurate timekeepers ever built by any civilization, as far as we know. The best of them would gain or lose less than 1 second over the entire age of the universe. To achieve this precision, the atoms are held in place by a carefully tuned lattice of laser beams, at temperatures of a few microkelvins. They are, at these temperatures, barely moving. They sit in the lattice like marbles in a carefully shaped grid, each one being interrogated at almost the exact same moment. These clocks can detect things no other instrument can detect. If you move one optical lattice clock up by 1 centimeter and leave another at the original height, they will show slightly different elapsed times after a day. The difference is incredibly small, but it is measurable. This is general relativity, Einstein's theory of gravity, operating in a laboratory on a tabletop. Time flows very slightly faster higher up, where gravity is a tiny bit weaker. The effect is real. The clocks see it. Atomic clocks also underpin much of modern life. The global positioning system, which lets your phone know exactly where you are, relies on a network of atomic clocks in satellites orbiting Earth. The satellites broadcast the time according to their onboard clocks, and your phone calculates its position based on tiny differences in when those signals arrive. Without atomic clocks, there would be no GPS. Without GPS, there would be no precise navigation, no Uber tracking, no satellite imaging, no weather forecasting of modern accuracy. All of this rests on cold. If the atoms in atomic clocks were not cooled, the clocks would not be accurate. If the clocks were not accurate, the satellites would not know the time. And if the satellites did not know the time, the maps in your pocket would not work. Cold is, in this quiet way, part of the infrastructure of modern civilization, and the applications of cold only multiply. Quantum computers, as we mentioned, operate at 10 millikelvin or below. These are temperatures colder than any natural thing in the observable universe. Companies like IBM, Google, and many others operate large arrays of dilution refrigerators, each holding a small quantum chip at those temperatures, each surrounded by layers of shielding and vibration isolation. The chips run calculations that would take ordinary computers years, using the strange quantum superposition of cold atoms and circuits. Whether or not these quantum computers will change the world in the big, dramatic ways that are sometimes promised, they are already doing physics that would be impossible in warm matter. They are exploring the edges of what computation can be, and they are doing it in a kind of quiet artificial winter, inside metal cylinders that hum softly in laboratories, pretending to be colder than anywhere in nature. All of this is made possible by cold. So, when you think of the coldest place in the universe, the correct picture is not a frozen moon. It is not a deep, dark nebula. It is a quiet laboratory on Earth, or a shoebox-sized chamber on the International Space Station. A soft hum, a cooled chamber, a cloud of atoms so cold that they share a single wave, sitting in a vacuum, surrounded by the ordinary warmth of the world. The universe is, mostly, a warm and active place. Stars burn, galaxies rotate, gas clouds collapse, the background glows at 2.7 Kelvin. Nothing in nature is colder than a few degrees above the absolute floor. Nature, left to itself, cannot reach deep into the cold. But here, in our quiet rooms, on a small blue planet in an outer arm of the Milky Way, a species of primate has learned to reach where the universe cannot. By tuning laser beams, by building refrigerators of exquisite subtlety, by patience and care and a long patient record of improvement, we have made matter colder than anything else in existence. In the next section, we will look at what happens there, at the strange behaviors of matter on the edge of absolute zero. Because it turns out that the cold hides secrets. Matter does not simply freeze. It transforms. It reveals things that warmer matter hides. Before we continue, a brief pause. If you are still with me, thank you. If this is helping you settle into sleep, that is exactly the purpose. You can close your eyes. You do not need to follow every word. The sound itself is enough. And if these long nights help you, consider subscribing. It costs nothing. It helps these slow journeys continue. Now, gently, let us look at what the coldest matter actually does. Part 5. The Physics of Impossible Cold. When matter approaches absolute zero, it stops being ordinary matter. It does not simply become colder. It becomes different. This is one of the most remarkable lessons of 20th century physics. That temperature is not just a number. That the rules which govern warm matter, the rules you learned in school about solids and liquids and gases, do not survive the journey to the bottom. Down there, in the deep cold, there is a realm where the familiar categories dissolve, where gases become waves, where liquids climb walls and flow without friction, where electrical currents run forever without losing any energy, where two isolated atoms, separated by a gap, share a single state, where the rules you are used to break down and newer, older rules take over. The rules of quantum mechanics, always there, always operating but usually hidden by the heat of ordinary life. Let us walk through what happens as matter is slowly cooled, step by step, temperature by temperature. At ordinary temperatures, like the temperature of your bedroom, atoms move rapidly. Solid matter holds its shape, but the atoms inside a solid are still vibrating in place, jiggling around their lattice points, never fully still. Liquids flow because the atoms can slide past each other. Gases expand because the atoms, only loosely connected, fly apart in all directions at great speed. As you cool matter, the motion slows. Gases condense to liquids. Liquids freeze to solids. The atoms hold their positions more firmly. Everything becomes quieter. Most substances, if you cool them enough, will turn into a solid. Water freezes at 273 Kelvin. Mercury freezes at 234 Kelvin. Oxygen freezes at 54 Kelvin. Nitrogen freezes at 63 Kelvin. Hydrogen freezes at 14 Kelvin. Even helium can, in theory, freeze, but only under very high pressure. At normal atmospheric pressure, helium never becomes a solid, no matter how cold you make it. Even at absolute zero, under normal pressure, helium remains a liquid. This is one of the first signs that something unusual is happening, something that does not fit the ordinary rules. Helium's refusal to freeze comes from quantum mechanics. Helium atoms are small and weakly bound to each other. Their quantum zero-point motion, the residual jiggling that even a perfectly cold atom still has because of the Heisenberg uncertainty principle, is enough to keep the atoms moving, even at absolute zero. Even when you remove all of the thermal energy, the quantum jiggling remains, and it is enough to keep helium liquid as long as the pressure is low. This is worth pausing over. Even at absolute zero, motion does not fully stop. There is always a residual, irreducible quantum jiggling. This is not a failure of cooling. This is a fundamental feature of reality. Particles cannot be completely still because they also cannot have a perfectly defined position. The uncertainty principle requires that if a particle is confined to a very small region, it must have significant momentum. And if it has significant momentum, it must be moving. This jiggling, the zero-point motion, is the irreducible minimum. You can cool a thing as close to absolute zero as you like, but there is always some whisper of motion left. Now, helium stays liquid. But when you cool it below about 2.17 Kelvin, something astonishing happens. The helium goes through a phase transition. It becomes what is called a superfluid. A superfluid is a liquid that flows without friction. Read that again, slowly. A liquid that flows without friction. No viscosity, no internal resistance. If you stir it, it stirs forever. If you set it moving around a loop, it circulates without stopping. No warm liquid can do this. No warm liquid, even honey thinned down, even the smoothest water, has truly zero friction. But superfluid helium does. Other strange things happen to superfluid helium as well. It can climb up the walls of its container, forming a thin film that flows over the rim and drips down the outside. It is not defying gravity. The thin film of superfluid is held to the walls by weak molecular attractions, and because it has no friction, it flows under any small pressure difference. If there is any gradient of pressure between inside and outside, the helium will simply flow until the pressures equalize. A container of superfluid helium will, if given time, empty itself completely, drop by silent drop over the rim, down the outside, onto the floor. A superfluid can pass through impossibly small holes. It can spin up vortex filaments that last forever, tiny whirlpools inside the liquid that do not decay. It can transmit heat by a strange wave-like process called second sound, in which temperature itself propagates like a wave. All of this happens because, at 2.17 Kelvin, the helium atoms enter a coherent quantum state. Large fractions of them occupy the same quantum state at the same time. And when many particles share a state, they stop behaving like a collection of individuals. They behave like a single, large, collective object. The liquid, in a sense, is not really a liquid anymore. It is a single entity, a single wave. This is the first of the weird things that happens as you approach absolute zero. A gas that refuses to freeze, a liquid that has no friction, matter that behaves as one coherent whole. But it is only the beginning. Helium-3, a rare isotope of helium with 2 protons and 1 neutron instead of 2, does something even stranger. When cooled to a few millikelvin, about 1,000 times colder than ordinary liquid helium, helium-3 also becomes a superfluid. But the mechanism is different. Helium-3 atoms pair up in a delicate dance, each atom finding a partner, and the pairs then enter a coherent quantum state together. The resulting superfluid has internal structure. It is richer, more complex, more subtle than the superfluid of helium-4. In helium-3, there are multiple distinct superfluid phases, different patterns of how the pairs behave, regions where the pairs are oriented one way, regions where they are oriented another, boundaries between them that behave like soft walls. Helium-3 in its superfluid state is an extraordinarily complex quantum fluid, one of the most intricate natural phenomena ever studied. One of the most beautiful phenomena in any superfluid is something called a quantized vortex. Take a bucket of ordinary water and stir it. You produce a whirlpool. The water rotates in a continuous range of speeds, faster near the center, slower near the edge, smoothly varying. Now take a bucket of superfluid helium and rotate it. The superfluid does not form a smooth whirlpool. Instead, it forms a specific number of tiny, precise vortex filaments, each one carrying exactly the same amount of rotation. If you rotate the bucket a little, you get a few vortices. Rotate it harder, you get more vortices. The vortices can only appear in specific, discrete amounts, each one a quantum of rotation. Scientists have photographed these vortex arrays. They look like tiny straight lines running through the fluid, arranged in neat, regular patterns. Each one is a stable structure that, once formed, persists for as long as the rotation lasts. In principle, forever. This quantization is a signature of the superfluid state. It tells us, without any doubt, that the fluid has entered a quantum coherent state, that it is behaving as a single macroscopic quantum object, not as a collection of individual particles. And it shows us, in physical terms, what quantum coherence looks like at large scales. There is also a phenomenon called the quantum Hall effect. It appears in very cold, very clean semiconductors, when a strong magnetic field is applied perpendicular to a thin layer of material. At certain precise conditions, the electrical resistance of the sample takes on discrete values, separated by large plateaus. The resistance can only be one of a specific set of values, determined by fundamental constants of nature. Nothing else. This is another case in which the universe reveals deep structure only in the cold. The quantum Hall effect cannot be observed at room temperature. It requires temperatures below a Kelvin, sometimes below a millikelvin. And it led, when it was discovered in 1980, to a new definition of electrical resistance based on constants of nature rather than physical standards. It won the Nobel Prize in Physics in 1985. More recently, physicists have explored even more exotic phases of matter at very low temperatures, so-called topological phases, in which the order is not defined by where the atoms are, but by abstract mathematical properties of their collective quantum state. These phases have different kinds of order. They cannot be understood through any classical description. They only exist in the quiet of deep cold. And there are fractional quantum Hall states, in which particles behave as if they had a fraction of the charge of an electron. Not because the electrons have really split, but because the collective quantum state is so rich that new kinds of effective particles emerge from it. These effective particles, called anyons, may someday form the basis of a new kind of quantum computer. Or they may simply be a beautiful illustration of how deep and strange the physics of cold matter can be. All of this is there. All of it is visible only when the thermal noise is low enough. Cold, once again, is a doorway. There is also, in the very coldest and quietest experiments, a question that has haunted physics for decades. Can cold reveal something about the nature of dark matter? Dark matter is the invisible substance that makes up most of the mass in the universe, but interacts so weakly with ordinary matter that it has never been directly detected. Any detection would have to come from extremely sensitive experiments, in which every possible source of background noise had been reduced. Cold is essential for those experiments. The colder the detector, the quieter the background. Cold detectors of various kinds, from supercooled xenon to supercooled germanium to supercooled crystals like those in Cuore, sit silently in deep laboratories around the world. Mines, mountains, tunnels, waiting, listening. So far, none have seen a clear, repeated dark matter signal, but they are watching. They will keep watching. Cold is the listening post of modern physics. And every year, the quiet grows deeper. And, again, the lesson is the same. When you cool matter this far, it stops being a simple thing. It reveals new structures, new behaviors, new phases. Superconductivity is another example. When certain metals are cooled below a critical temperature, they lose all electrical resistance. A current started in a loop of superconductor will flow without losing energy, forever. No heat is generated. No power is needed to maintain the flow. The first superconductor, mercury, was discovered by Kamerlingh Onnes in 1911. Its critical temperature is about 4 Kelvin. Since then, many other superconductors have been discovered. Some require cooling to only a few Kelvin. Others, the so-called high-temperature superconductors, work at temperatures up to 100 Kelvin or more. Still cold by human standards, but warmer than liquid helium. Easier to maintain. Superconductors are not merely good conductors, they are something different. They expel magnetic fields from their interior, a phenomenon called the Meissner effect. They can carry currents that would melt ordinary wires without generating any heat. They are used in the magnets of MRI machines, in particle accelerators, in sensitive detectors that can measure the smallest magnetic fields from a single human brain. And they are possible only because of cold. When the temperature rises above the critical temperature, superconductivity vanishes. The metal goes back to being an ordinary conductor, with ordinary resistance, ordinary losses. The transition is sharp, like a phase change. Warm matter, ordinary. Cold matter, new. Then there are Bose-Einstein condensates, which we met earlier, a cloud of atoms cooled to nanokelvin temperatures, where the individual atoms merge into a single shared quantum state. In a Bose-Einstein condensate, the atoms are not distinct. They are overlapping waves that together form one coherent wave. You can photograph this wave. You can watch it ripple. You can split it in two and bring the halves back together, and they interfere with each other, producing patterns of bright and dark stripes, just like light waves do. In a Bose-Einstein condensate, quantum mechanics, normally invisible, is on display. You can see wave functions in the laboratory, and in the very coldest condensates, at picokelvin temperatures, the waves are so pure, so quiet, that the tiniest perturbation is detectable. A gravitational force, a passing planet, a vibration in the laboratory. All of it registers in the condensate. This is one reason these ultra-cold systems are of interest for fundamental physics. They are exquisitely sensitive detectors of the most subtle forces. There are also Fermi condensates, made from fermions rather than bosons. Regular atoms like helium-3 are fermions, and fermions, unlike bosons, cannot share the same quantum state. So how can fermions form a condensate at all? The answer is that fermions can pair up, two at a time, and each pair then behaves like a boson. The paired-up fermions can share a state. They can form a collective quantum object. This is exactly the mechanism behind superconductivity, where electrons pair up into what are called Cooper pairs and become superconducting. In ultra-cold fermionic gases, we can see and manipulate this pairing directly. Fermionic condensates have been made at temperatures of a few nanokelvins. They are the other great success of ultra-cold physics. What unifies all of these phenomena is a single idea. At low enough temperatures, quantum mechanics stops being a secret. Usually, quantum effects are tiny. They happen on the scale of atoms, inside individual particles, hidden by the thermal noise of warm systems. But when you remove that noise, by cooling the system, the quantum effects come out of hiding. They grow to macroscopic size. You can see them. You can manipulate them. You can use them. Cold is, in this sense, a doorway, a way of revealing what was always there. The quantum world is not a separate world from the one we live in. It is our world, but we cannot see it because our world is too warm. Turn down the heat, carefully, patiently, and the quantum world becomes visible. This is part of why scientists are so interested in the coldest possible temperatures. It is not just an engineering challenge, it is a window. Each new millikelvin of cooling shows us a little more of the universe's hidden structure. And there is another reason. Cold is essential for any precise measurement. Thermal noise, the random jiggling of particles at finite temperature, drowns out small signals. If you want to measure a faint vibration, a tiny magnetic field, the wobble caused by an atom decaying next door, you must reduce the noise. And the best way to reduce thermal noise is to cool your detector. Every one of the most sensitive physics experiments in the world relies on cold. The detectors for gravitational waves use mirrors cooled to a few Kelvin. The detectors for dark matter use vats of liquid xenon maintained at 170 Kelvin or below. The detectors for neutrinos use cold water, cold ice, or cold argon. The best atomic clocks use laser-cooled atoms. Cold is the quiet room that lets us hear the universe whisper. There is a subtlety to cold that is worth one more mention. Cold is not uniform in its effects. Matter does not gradually and smoothly change as you cool it. Instead, at certain temperatures, called critical temperatures, there are sudden transitions. One moment the matter is one thing. The next moment it is something else. Phase transitions. Water freezing at 273 Kelvin is a phase transition. The water does not gradually get firmer. It is liquid, and then it is solid. There is a specific temperature at which the change happens. Superconductivity is a phase transition. Above the critical temperature, the material is a normal conductor. Below, it is superconducting. The transition is sharp. The superfluid transition of helium-4 at 2.17 Kelvin is a phase transition. Each of these transitions is a discrete event, a discontinuity in the behavior of matter. And the pattern of phase transitions as you cool from warm to cold is part of the signature of what a substance is, at its deepest level. Materials with different internal structures have different patterns of phase transitions. Learning those patterns is learning how matter is organized. And the very coldest temperatures, the ones approaching absolute zero, are where the most exotic phase transitions happen. Phase transitions you cannot see in ordinary conditions. Phase transitions to quantum liquids, to Bose-Einstein condensates, to fermionic superfluids, to topological phases that were only recently discovered and are still being explored. The cold universe is a catalog of states that do not exist anywhere else, and we have only just begun to explore it. If you could step into a cold laboratory, a laboratory at 10 millikelvin, you would need every kind of protection imaginable. The air you breathed out would instantly freeze. Your body would radiate warmth like a furnace. Your equipment would need to be isolated from every source of vibration and heat. A single breath, a single footstep, a single laser beam reflected off a passing fly would heat the sample by more than its total thermal energy. Cold laboratories are extraordinarily quiet. They are nested inside vacuum chambers, wrapped in layers of insulation, shielded from magnetic fields, mounted on tables that float on air to isolate them from vibration. The final sample, at the coldest point, is the size of a coin. Around it, everything is designed to leave it alone, to preserve the delicate quantum state, to let the cold continue to reveal. When we talk about the coldest place in the universe, we are talking about these small, quiet coins of matter. Each one, inside its own chamber, is colder than anywhere else in the universe, colder than any star ever made, colder than any nebula, colder than empty space itself, by factors of billions. And they are here, on our planet, right now, in dozens of laboratories, being studied by patient scientists. In the final section of our journey, we will step away from the present and look at the future. At the long, dark era that will come, billions and trillions and far more years from now, when the universe itself, the whole vast universe, approaches the cold that these laboratories have only briefly touched. Because the universe is slowly, steadily, inevitably growing cold. And the story of temperature does not end with what we have made. It ends with what the cosmos will become. Let us now look forward, far forward, into the long final chapter of the universe. Part 6. The Ultimate Cold. Heat, Death, and Eternal Silence. The universe was born hot. In its first moments, every particle was packed together in a dense, glowing plasma, billions of degrees, trillions of degrees, densities, and temperatures that no laboratory can imagine. Then the universe expanded, and it cooled, and it has been cooling ever since. The cooling is slow now. The cosmic microwave background, that ancient light we talked about earlier, has been dropping in temperature for nearly 14 billion years. Right now it sits at 2.725 Kelvin. But it is still falling. Very slowly, as space continues to expand, the background temperature drops, and this cooling will continue. Forever. The universe, according to our current best understanding, is not only expanding, it is expanding faster and faster. A mysterious force called dark energy, the nature of which is one of the great unsolved problems in physics, is pushing space itself apart at an accelerating rate. Distant galaxies, each already moving away from us, are receding faster and faster. The farthest galaxies we can see today will, in time, move beyond our reach. Their light, red-shifted by expansion, will stretch into wavelengths we cannot detect. They will, in effect, vanish. The universe is becoming lonelier, and, crucially for our story, it is becoming colder. Let us walk forward in time, slowly, patiently. Let us imagine the universe many ages ahead. Right now, we live in the stelliferous era, the era of stars, galaxies full of bright burning suns, making new elements in their cores, living out their short or long lives, and eventually dying. Our sun is in the middle of its life. In about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a slowly cooling white dwarf. The Earth will either be consumed or left as a burnt cinder. It depends on details. Either way, our home will not survive. But the stelliferous era itself will continue for a long time after the sun is gone. Other stars will be born, live, and die. New stars will form in the dense clouds of old galaxies. Small, faint stars will burn for hundreds of billions of years, their fuel stretched by their slow metabolisms. Eventually, though, the gas of each galaxy will be exhausted. No new stars will form. The existing stars will one by one exhaust their fuel and die. By about 100 trillion years from now, the last star is expected to burn out. The night sky across the entire universe will grow dark. This is the end of the stelliferous era. It is also the beginning of something called the degenerate era. In the degenerate era, there are no more stars, only stellar remnants, white dwarfs cooling in the dark, neutron stars spinning in silence, black holes of all sizes consuming any matter that falls in. The universe becomes a graveyard. Most of its light source has gone out. What remains is a catalog of dead things, slowly radiating what little energy they have. And they do radiate. A white dwarf is a hot, compact object when it forms. It can be as hot as 100,000 Kelvin. Over time, as it radiates heat into the surrounding space, it cools. After 1 trillion years, it might be 1,000 Kelvin. After 10 trillion years, it might be a few hundred Kelvin. Eventually, over time scales stretching into trillions of years, the white dwarfs cool to temperatures approaching the background of the universe, cold enough to match the fading microwave background, cold enough to disappear into the night. A neutron star, likewise, cools over time. A black hole, on the other hand, does not cool in the ordinary sense. It slowly evaporates through a process called Hawking radiation, in which tiny amounts of energy are leaked from the boundary of the black hole into the surrounding space. Hawking radiation is extraordinarily faint for any black hole larger than about the mass of a mountain. For astrophysical black holes, the rate of evaporation is slower than you can easily imagine. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. A black hole with the mass of our galaxy would take far longer. Let us pause at that number. 10 to the 67. A 1 followed by 67 zeros. That is many trillions of trillions of trillions of times the current age of the universe. It is, in a very real sense, a number so large that the word incomprehensible is the closest thing to a description. To get a feeling for this number, try the following. Imagine every second that has passed since the universe began. Every second since the Big Bang, through the formation of galaxies, through the birth and death of stars, through the origin of the Earth, through all of biological history, through every human who has ever lived, right up to this moment. The number of seconds is large. It is about 4 times 10 to the 17th. A 1 followed by 17 zeros. That number, enormous as it is nothing compared to 10 to the 67. The difference is a factor of 10 to the 50th. That is, the time to evaporate a sun-sized black hole is 10 to the 50th times longer than the entire history of the universe so far. If the current universe were 1 second old, the black hole would evaporate in about 10 to the 50th seconds. A number so vast that the human mind has no intuition for it. But even this is not the longest timescale in cosmology. The largest black holes, those at the centers of galaxies, weighing billions of solar masses, take even longer. They may persist for 10 to the 100th years before finally evaporating. A Google years, a number so huge that every atom in the observable universe would be less than a grain of sand in a mountain of this time. And when the black holes are all gone, what remains? A diffuse sea of radiation, spread thinly across a universe that has continued to expand. Occasionally, a single photon traveling through the emptiness. Occasionally, a single proton thought by some physicists to be unstable on very long timescales, which eventually decays into lighter particles. The universe, at this point, is nearly empty. Whatever matter is left is spread so thinly that the distance between individual particles exceeds the size of the current observable universe by factors beyond imagining. There is no temperature here in the ordinary sense. Not enough particles to have an average kinetic energy. Only the faintest, coldest whisper of the cosmic background, red-shifted to wavelengths so long they are almost undetectable. Some physicists speculate about what might happen next. Perhaps, after enough time, a quantum fluctuation could trigger a new Big Bang. Perhaps a new universe might emerge from the empty vacuum. Perhaps, in an infinite future, any configuration of particles that is possible will eventually occur, and occur again and again, producing strange chance arrangements, including, occasionally, arrangements that look briefly like galaxies or stars, or even, for a moment, thinking beings. These are called Boltzmann brains, and they are, mostly, a philosophical curiosity. Whatever happens, it will happen in a universe that is cold, colder than you can easily imagine, colder than any laboratory, colder than any nebula, nearly still, nearly empty, almost at the floor. The ultimate cold is not a single place. It is not a single moment. It is a direction and a destination. A direction in which the universe has been traveling since its first second. A destination it will approach forever without ever quite reaching. Yet, eventually, even the smallest black holes evaporate, and then larger ones, and then the supermassive black holes at the centers of former galaxies. One by one, they leak away their mass into the vacuum, until nothing remains but a faint puff of radiation, spread thinly through space. This is the black hole era. It stretches from about 10 to the 40th years to roughly 10 to the 100th years. Almost inconceivable lengths of time, during which the only warmth left in the universe comes from the slow evaporation of black holes. The rest is cold, and the background is dropping, dropping, dropping. As the universe expands, the cosmic microwave background stretches with it. Its wavelengths grow longer. Its temperature falls. Where it was 3,000 Kelvin a few 100,000 years after the Big Bang, it is 2.7 today, and it will be 1 Kelvin in perhaps 100 billion years, and 1,000th of a Kelvin after that, and 1,000,000th of a Kelvin further on. In the long future, the background itself will drop below the temperatures that cold laboratories on Earth have achieved. Let us say that again. In the far future, the entire universe, every corner of space, will be colder than a laboratory on Earth in the 21st century. Every star will be gone. Every black hole will eventually have evaporated. The light of the Big Bang, once hot enough to ionize all matter, will have faded into a dim whisper, and then to silence. This is the heat death of the universe. It is not a fiery death. It is the opposite. It is a cold, slow, quiet, almost peaceful fade. An approach to equilibrium with nothing. A universe in which no temperature differences exist, in which heat cannot flow, in which no work can be done, no thought can be sustained, no motion can propagate. A universe at rest. The word death is perhaps misleading. Nothing is being killed. The universe is simply cooling to its final state. A state in which all the differences that allowed for stars and planets and life have been smoothed out. A state in which the map has become featureless. Temperature in such a universe continues to fall, but never reaches zero. The third law of thermodynamics holds. Absolute zero is unreachable, even for the universe as a whole. Instead, the universe will approach it asymptotically. It will get colder and colder and colder forever, without ever arriving at the floor. And it will be silent. Think of it. A universe, vast beyond imagination, so empty that the distance between any two particles exceeds the size of the entire observable universe today. Every location, cold. Every location, still. Photons so redshifted that their wavelengths are measured in billions of kilometers. Temperatures so low that our current laboratory records, which seemed so astonishing, would feel like the surface of a star by comparison. This is the ultimate cold. The universe itself cooled nearly to absolute zero across the whole of existence. There is a certain beauty to it, a certain stillness. The same stillness, in a way, that you might feel on a very cold night in the mountains, when the air is clear and the stars are sharp and there is no sound but the faint crunch of snow. A stillness of completion, a stillness of rest. And there is a stranger thought still. If the universe is truly heading toward this state, then every moment of warmth, every burning star, every living creature, every second of motion is an exception. A pocket of warmth in a universe that is, on the whole, slowly cooling. The warmth of your hand, the warmth of your bed, the warmth of the earth is borrowed. Borrowed from the slow unwinding of an earlier, hotter moment. Borrowed from the gradient that will, eventually, smooth itself out. Every warm thing is a temporary thing. Every still thing is also temporary in a different way, slowly becoming still on a scale you cannot perceive. This is the final lesson of the story of cold. That cold is not just a state. Cold is a direction. Cold is where the universe is going. Warmth is a kind of memory. A last breath of the early, hot moment, running out of air. You and I and everything we know live in the warm memory. And it is beautiful because it is temporary. It is precious because the quiet is coming. But there is no need to feel sadness about it. The time scales are so long that they have no meaning for a single human life. You will not witness the stelliferous era's end. You will not witness the cooling of the last white dwarf. You will not witness the evaporation of any black hole. These things unfold over time scales so much longer than human history that they are, in a sense, irrelevant to the small warm story of your life. What matters in the middle of all this is that the universe, briefly, allows small warm creatures to exist. Creatures that can think about cold. Creatures that can build machines colder than any nebula. Creatures that can imagine the future of the universe and write the imagining down and tell each other about it on quiet nights so that others can lie in warm beds and think about the cold, gently for a little while before falling asleep. That is remarkable. That is what the universe contains at this moment. Small, warm beings capable of considering the very long cold that is coming without being afraid of it. Let us take now one last slow tour. Let us gather what we have seen tonight. We began with the simple cold that humans have known. Winter mornings, kitchen freezers, Antarctic ice, all of it, warm by the standards of the universe. Only a few dozen degrees below freezing, on a scale that stretches for nearly 300 Kelvin down to absolute zero. A narrow band, a thin slice. We stepped outside the Earth, and we discovered that space has a temperature of its own. Not because of the vacuum, which is near empty, but because of the ancient light of the cosmic microwave background, bathing everything in 2.725 Kelvin. The echo of creation, the floor of passive cooling in the universe. We visited the cold places in our solar system. Neptune's moon Triton at 38 Kelvin. Pluto at 33. The permanently shadowed craters of our own moon at 25. Colder than anywhere a human has ever walked. We traveled further out, past our solar system, and found the molecular clouds that birth stars, cold pockets of hydrogen gas at 10 Kelvin. And we found the Boomerang Nebula, a dying star in the constellation Centaurus, 5,000 light-years away, whose expanding gas is colder than the cosmic background. 1 Kelvin, 1 degree above absolute zero. The coldest natural place in the universe that we have ever measured. We returned to Earth and traveled down into human laboratories. We walked through the history of cold, from the first liquefied helium at 4 Kelvin to the first laser-cooled atoms at microkelvin temperatures, to the first Bose-Einstein condensate at 170 nanokelvin, to the picokelvin clouds on the International Space Station, to the 10 millikelvin ton of tellurium deep under an Italian mountain. We saw how humans, patient primates on a small warm planet, have pushed matter colder than the universe itself has ever managed. We looked at the strange things that happen when matter approaches absolute zero. Superfluids that flow without friction and climb their own walls. Superconductors that carry electricity forever. Bose-Einstein condensates in which many atoms share a single wave. Quantum phenomena, usually hidden, brought into plain sight by the stillness of cold. Cold as a doorway. Cold as a quiet room that lets us hear the universe whisper. And finally, we looked forward, to the slow cooling of the entire universe, the death of stars, the evaporation of black holes, the approach of the cosmic background to absolute zero, the silent, empty, nearly still state that awaits in the far distant future. A cold that the universe itself will take incomprehensibly long to approach, and will never quite reach. That is where we end tonight. Not in a place, in a direction. Cold is where the universe is flowing, and that is, in its way, peaceful. Now, for a final moment, let us return to where we started. You, here, tonight, warm in your bed. The night is quiet around you. Perhaps there is a sound of soft traffic outside, or the wind, or rain. Perhaps there is only silence. Your body is warm. Your breath is warm. The earth beneath your home is warm. The sun, though far below the horizon, is still burning, still sending warmth that you cannot feel but which, yesterday, heated the ground you stand on. The universe, for a little while, is full of warmth. You are made of particles that are moving. Your atoms are jiggling. Your blood is flowing. Your thoughts are forming, falling apart, reforming. All of this is motion. All of this is temperature. All of this is the opposite of what we have talked about tonight. And it is a gift. The cold is coming. Slowly. On timescales that do not matter. But it is coming. And every warm moment in the meantime is a small, temporary, precious thing. So rest now. Let your warmth continue a little longer. Let your breath slow. Let your thoughts quiet. The universe will get to its final cold in its own time. You do not need to do anything about it. You do not need to think about it. You can simply be warm, here, tonight, with the slow sound of this voice and the soft weight of your blankets and the wide, gentle dark of the room. If this night has helped you, consider subscribing to the channel. It is the smallest thing, and it helps keep these slow journeys alive. No ads mid-video, no loud jumps. Only long, quiet explorations like this one night at a time. And if you are already here, thank you. Thank you for being one of the small, warm creatures in the universe, choosing to think about cold for a little while before sleep. Rest now. Let the warmth hold you. The cold will wait. It always does. And tonight, it is very far away. Good night.